Good day everyone, I'm Dane Suan and today I will be presenting the research on petrology and geochemistry of intrusive rocks in the Tanjung area. This study focuses on understanding how these rocks formed, what materials they came from, and what they can tell us about the region's geologic history and tectonic activity. This study will cover the background and objectives of the study, the geological setting of the Tanjung area, and the materials and methods used, and also the petrographic and geochemical findings, and finally, the conclusions about the origin and evolution of the rocks in the area. Tanjung area lies within the Bureau Intrusive complex, which has experienced arc continental collisions since the Tertiary. This study aims to understand the characteristics of the rocks in this region, especially their mineral content, chemical makeup, and how the magma that formed them originated. Although some tectonic studies exist, detailed geochemical investigations have been limited, especially in this specific area. So, the geology of the South Sulawesi is shaped by a history of tectonic activity, including subduction zones and continental collisions. The Bureau Intrusive complex includes rock formations from the Middle Eocene to Miocene formed during these events. The presence of flask, volcanic rocks, and limestone indicates a dynamic environment involving uplift, volcanism, and sedimentation. So this map shows where the Bureau Intrusive complex is located. It highlights various rock units and tectonic features, helping us understand the regional geological framework where these rocks formed. For the materials and methods, the researchers collected 31 samples from various locations in the Tanjung area. Petrographic analysis was done on 8 of the samples using a polarizing microscope to study the mineral content and textures. For chemical analysis, 18 samples were tested for major elements using X-ray fluorescence and 13 for trace and rare elements using inductively coupled plasma and mass spectrometry. Researchers compared the results with previous studies to ensure accuracy and relevance to the regional context. For the results and discussion, the first one is the petrography. Petrographic analysis revealed two main groups of rocks, including plutonic and volcanic rocks. The plutonic rocks such as granite and granodiorite display granular textures, which means they cooled slowly underground. The volcanic rocks like trachyte and basaltic trachyandesite show porphyritic textures, meaning they cooled more quickly and contain large crystals embedded in the fine matrix, and the researchers also found signs of alterations like chlorite and cerisite, indicating the rocks were affected by hydrothermal fluids after they formed. So this presents the photomicrographs of the plutonic rocks under a polarizing microscope. This rock cooled slowly underground, allowing large crystals to grow. The textures observed are mainly granular, with interlacking mineral grains that indicate slow crystallization within a magma chamber. The granodiorite and granite samples show well-formed quartz, plagioclase, and orthoclase. In some areas, researchers see biotite and hornblende, which are mafic minerals that crystallize early. The monzonite and quartz monzonite samples also show similar textures, although the mineral proportions differ slightly. And on this slide, it displays the photomicrographs of volcanic rocks from the Tanjung area. These rocks erupted to or near the surface where they cooled quickly. The textures are dominantly porphyritic, meaning large crystals called phenocrysts are embedded in a fine-grained groundmass. The phenocrysts observed include pyroxene, plagioclase, and hornblende. These minerals crystallized earlier while the magma was still underground. The groundmass, which cooled quickly during eruption, consists of very small crystals or volcanic glass. Some secondary alterations were also observed. Chlorite and clay minerals are replacing the original mafic minerals, particularly in the matrix. This again suggests that the rocks were exposed through hydrothermal fluids or low-grade metamorphic conditions after their eruption. So this slide presents the geochemical analysis for major elements. From the chemical analysis, It is found that the rocks belong to the calc-alkaline and succinic series, which are typical of volcanic arc environments. The Harker diagram shows how some elements decrease as silica content increases, especially the calcium oxide, magnesium oxide, and iron oxide. This pattern suggests that the magma underwent fractional crystallization, where certain minerals crystallized and were removed from the melt, changing its composition over time. So these slides present the Harker diagram of the sample. As you can see, each line on the graph represents a different major element. As you move to the right, toward higher silica, you can see some elements drop, showing the magma's evolution through crystallization. For the geochemical analysis of trace elements, trace element patterns further support a subduction-related origin, and both plutonic and volcanic rocks are enriched in elements like rubidium and barium, which are mobile during fluid-rock interactions, a process common in subduction zones. They also show enrichment in lighter elements like lanthanum and cerium. The negative anomalies in niobium, strontium, and europium indicate that the magma likely interacted with continental crust or plagioclase was removed early during the crystallization. This spider diagram shows how trace elements compare to what's expected in the Earth's mantle. Peaks and dips indicate how the magma interacted with the surrounding crust. The REE diagram highlights enrichment in light REEs and drop in europium, suggesting plagioclase fractionation. Next is the magma origin. By analyzing the mineral content and chemical ratios, the researchers found that the plutonic rocks are mostly I-type, which means they originated from igneous sources. The volcanic rocks, however, show characteristics of both I-type and S-type magmas, suggesting that some sedimentary materials were involved in their formation. This means that the magma likely came from partial melting of the upper continental crust during the subduction. For the geodynamic setting of this study, based on tectonic discrimination diagrams, the rocks in the Tanjung area mostly plot within volcanic arcs and seen collisional fields. This supports the idea that the magma was formed in an active subduction zone and later influenced by continental collision. Some of the data also suggest that after the collision, magma generation involved input from the lithospheric mantle. So with the use of these diagrams, it helps us understand where the magma formed. By comparing specific trace elements, we can identify whether the rocks came from subduction zones, collision zones, or within plate settings. And this data is clustered in arc-related fields. To conclude this presentation, the intrusive and volcanic rocks in the Tanjung area are predominantly calc-alkaline, reflecting magmatic activity associated with convergent plate boundaries. The geochemical data indicate that the rocks exhibit both I-type or igneous mantle-derived and S-type as sedimentary crust-derived signatures. It suggests a mixed magma source, and this dual nature implies that the magmas were influenced by both mantle melting and assimilation of crustal material during ascent. The mineralogical analysis, particularly the presence of hornblende, biotite, and plagioclase, supports a subduction-related magmatic origin. The fractional crystallization process is evident from the systematic variation in major and trace elements, indicating progressive magma evolution. Additionally, the crustal contamination is inferred from elevated silica content and isotopic ratios, highlighting interactions with continental crust during the emplacement. This concludes my presentation, and this research presentation helps us to understand how magmas form and evolve during tectonic processes like subduction and collision. That's all, and thank you.